I think someone hacked my parent hacked my binder when I thinks that it's not with my backpack. But anyways, point is for some reason my lab disappeared.
You left your lab Friday in foods class. All right, ladies and gentlemen, you can hear me clap one time. You can hear me clap twice. Okay, go ahead. That's yours. Let's go ahead. Let's go ahead and answer this question. It says, why do we have night and day? So why is it that we think we have night and day? Go ahead.
Because the earth rotates. That's the largest answer.
Yeah, because the earth rotates. I like that a lot. Yep.
Okay, because the earth revolves around the sun.
Gentlemen, I don't want you doing that today, please. We're recording this lesson. Yep.
And as we revolve around the sun, we are spinning. Like, you know what I'm saying?
I do. It's called rotating.
Yeah. What he said, and as we rotate, we gets pushed to the other side, so we don't get sunlight, and then the other side gets more sunlight.
I like that. So we've got two things going on. As we are revolving, write this down, please. As we are revolving around the sun, and how long does it take the earth to revolve one time around the sun?
Around 365.
Around 365 days. 365 days. Okay, as we are revolving around the sun in 365 days, we are also rotating once every, don't blurt at me, raise your hand, we're rotating, Austin, once every 24 hours. Okay, once every 24 hours. I don't like that anymore. When we are facing the sun, this equals daytime.
What if the earth stopped rotating?
Good question. Someday it will. When we are not facing the sun, this equals nighttime. Marius had a really good observation. He said, imagine when we get to the point where we are no longer rotating. And that is happening. Every day, we are slowing down a little bit more in our rotation, and that's because of the pull on the moon and the water that we have on our planet. And so imagine if you had a basketball, and that basketball was filled halfway with water. And you roll that basketball down the sidewalk. What will happen to the water in that basketball?
It'll just keep going like this.
Yeah, it might slosh one way, then the other way, and then the other. And eventually that sloshing water is going to slow down that basketball and make it stop rotating.
Will that happen while I'm alive?
That will not happen while you were alive. No, yes, that will not happen when you were alive. But when it does happen, imagine a planet where we have perpetual nighttime on one side and perpetual daytime on the other. And probably where we would want to live would be right at that boundary, right? Right as close as we could be to where dusk and day is starting. Yeah, Aron.
Whether it's perpetual or not. Arguably, things like changing every half year.
We would be caught in a tidal lock where only one side of the planet would always be facing the sun.
So what would happen now?
I don't really know. I think we should get.
Okay. All right. Other questions on that? That is why we have daytime and nighttime. It takes us 365 days to revolve one time around the sun, that's 1 year. And every single day, we are rotating once every 24 hours. So, just a second, check for understanding. If I was to revolve around this classroom, how many times would I need to rotate completely one time in order to get all the way back to the beginning?
Yeah.
How many times? 365. I would have to go around 365 times like this with every step. 365, right? 365 of those rotations to get all the way back to where I began. Question.
Who taught the first teacher?
Who taught the first teacher?
Oh my.
I don't have that information. That's a good question. Thank you for asking. All right, ladies and gentlemen, I wish that we could go in this wonderful discussion. Unfortunately, I do not have time to do that. I need to know how many people, if you were not here on Friday, I need to have you take a Reasons for the Seasons lab, and then we have got the material that you need set up in the back. You are going to go back there and work as a group to finish this lab, okay? So if you were not here on Friday, you are going to pick up one of these Reasons for the Seasons lab. Mrs. McGrain is screencasting what we're doing so that you can then watch this when I post it on this slide tomorrow. So one more time, if you were not here on Friday, you're grabbing a lab and you're going into my prep area, please, to work on it as a group. Shut the door behind you, please. I don't know why he's going in there with a pink piece of paper. How did you remember this?
I have good long-term memory, but I can't remember. I have good long-term memory.
Okay. Let's go ahead and open up your lab, please, from Friday. If you could please go ahead and open up the lab from Friday, I would greatly appreciate it. What, dear? Yeah, you can go to the bathroom. Please make sure that you come back, though, as soon as you can so that you don't lose this information for the exam. So, on Friday, but you can't see this. On Friday, we went ahead and looked at a lab which was called the Reasons for the Seasons. The first part, which was part 1, are you looking for this lab? Yeah. Okay, were you here on Friday? Could you please grab that one? And everybody is in there working in the lab right now. I know, that's okay. All right, so could you please look at the 2 photos? Where are you going, man? Okay, so look at the 2 photos, right? The information that you gathered, and can someone please tell me what were the measurements that we got in January or July? Because when we first started, we had 4 friends that said, hey, I think this is why we have the reasons, or the reasons why we have the seasons. And the biggest misconception is that everybody thinks we are closer to the sun in the summertime and farther away from the sun in the wintertime. But when we took the measurements, what did we find out? Austin. 18.5. And in July, it's 18.2. And so if something is larger, that means it is closer to us when we take a picture of it. If I look at Grant's head and I squish it between my fingers, I say, crush you. And then I come closer, the closer I get, the larger he gets, okay? So when we see something large like 18.5 compared to 18.2, we know that we are actually closer to the sun when? We're closer to the sun in January, which is the middle of winter. So on that piece of paper that you picked up on the way in, pink or white, you will see that there are two things in there. It'll say just the facts. So what we're going to do right now is we're going to take some notes on that piece of paper. Aron, could you put that piece of paper up in the air so that I know that you know what I'm talking about? A deeper look at the seasons. Yours is pink. All right. So we're looking at where it says the facts. And the first fact that we're filling in says we are actually closer to the sun in our orbit during our winter. So could you please write this down right here where it says number 1? We are actually closer to the sun in our orbit during the winter time. And we noticed that from the measurements that we took in our lab that they are now hopefully doing in the back room. And we can also see that in our picture that I've given you here. This is a picture where we have the sun. I didn't hear what you said. What did you say? Okay, then that's them not using their time wisely. Right now, my concern is right here with you. So I've got June, and in June, and then we're comparing the picture of the sun in December. And we see that in June, the sun is just a scotch smaller than it is in December. And so because of this, we understand that we are actually closer to the sun in the middle of winter. Now, another thing to think about is this. If it is winter where we are in the northern hemisphere, what season is it going to be in the southern hemisphere? Summer. Now, if we were actually closer to the sun in summer, it would be summertime in the northern hemisphere and the southern hemisphere. And that's not the way it is on our planet. When it is summertime in the southern hemisphere, it's winter time. Summertime in the northern hemisphere, it's winter time in the southern hemisphere. And so if it were true that we were actually closer to the sun in the middle of July, then it would be warm and summertime throughout the entire world. If we look over on this side of our picture, we will see that what's called aphelion, which is the farthest away in our orbit, we're about 152 million kilometers from the sun. When we are closest to the sun in our orbit, in something called perihelion, we are only 147 million kilometers. So we are much closer here, even though it is colder in the northern hemisphere. But that must mean then that it has nothing to do with the distance we are in our orbital path. Natalie, I think one of our friends in the beginning of this journey that we took together, that was what she thought. That's what a lot of people think. That's one of our biggest misconceptions. All right. And so let's go ahead and look at seasons fact number 2. Fact number 2 that you're going to put on that paper, Aron, is that the Earth's axis has a fixed tilt, which means it stays in place. Okay, it's fixed. And it's fixed at 23.5 degrees. It's always pointed at the Polaris star or Polaris star. You need to write this down, bud, which is called the North Star. Okay, so in my lab, I asked you to go ahead and during part of the lab, and I'll use my lamp as a demonstration, I said to go ahead and take your little planet on a stick, and you were going to tilt it and make sure that the axis was always pointed toward the North Star, which on my classroom is over there on the wall. And so then I said, leave it that way, and then orbit the sun. And as we do that, we can see that the angles of light are shifting and changing on the planet. The northern hemisphere is getting less light, while the southern hemisphere is getting more light. And there's also a period of time when we get something that's called the equinox. Has anybody ever heard of equinox? Equinox is when we get equal amounts of sunlight and nighttime on the planet. In a 24-hour period, This is the time of the year where you get 12 hours of daylight and 12 hours of nighttime. For us this year, it's coming March 20th. We're going to have 12 and 12. And then every moment after that, throughout summer, you get a little bit more daylight and a little bit less nighttime. So we have our shortest night times and our longest day times. It doesn't mean that 24 hours is longer. It just means in that 24 hours, it's broken up into more daytime hours and less nighttime hours. Right now, we're flipped the other way. We've got more nighttime hours and less daytime hours. Oh, it's so depressing. But March 20th, it'll be equal, and then we're getting a little bit more daylight during the 24-hour period. Yay! All right. So it's important to note that the Earth does not wobble or tip back and forth. And you saw this right here on this particular graphic. It's always stuck at the same angle, 23.5, 23.5. Okay, and we see that right there. Question, I'm so sorry, Perseus. Very good question. We don't know if something hit us. I would assume that it did, because if you look at Neptune's angle, Neptune is all the way like this. Neptune actually rolls like a bowling ball through the solar system. And so we're assuming something hit it. We know that there was a Mars-sized planet that hit the Earth, and from that we formed the moon. So that might have been the impact. But for whatever it is, it got tilted. Now, it's important to note that this tilt can periodically change over long periods of time. Like every 5,000 years, the tilt slightly kind of changes just a little bit. But we're not talking about long periods of changes. We're talking about in 1 year's worth of time, that tilt is always fixed. Okay, that's what I want us to focus on. It's fixed at 23.5. Are we good? Okay. So then let's go ahead and look at the cause of the seasons. So we started talking about what the facts were. Now let's write down the causes. Cause number 1, write this down. The fixed tilt changes angles of light that hit certain regions, I'm going to say, of the planet or of our planet. It is those different angles of light, whether they are direct or indirect, that give us different intensities of light. And these then give us different temperatures at different areas of the planet. So it's how intense the light is that changes the temperature, whether it being at the equator or being by the north or south poles. This was shown in our lab over here when I asked you, and that's what they're doing in the back with their graph paper, I asked you to take a flashlight and give me a direct angle straight down on the graph paper. This direct angle would have given you a smaller circle of light. This would be representative of this situation right here, where we have the sun in the summertime going over its highest peak, so noon, it would be directly overhead and it would be very intense at noon. You go out and you see the sun way up high in the horizon, shining directly overhead. This means that for this example, we had less squares underneath this light. Those less squares meant that more energy was on each square. I'm just going to say energy with a circle, more energy on each square. And if there was more energy on each square, what would the temperatures be like? What would the temperature be like? They would be warmer. That would be a much warmer part of the land. And so if we look down in this area, we would see that that ties into summer. Summer would be a more direct sunlight, very intense, warmer, more energy from the sun hitting us in a smaller part of the world. On the other side, if we look at something like a 45-degree angle or even a 20-degree angle, that same energy is now spread over a much larger area. And so you're going to have more squares, which is going to be less energy per square, less E per square, and that is going to be cooler temperatures on that land, which would be something like a winter time. That is showing in this part of the lab that you did. The sun doesn't quite get all the way up in the sky. It's a little bit lower in the horizon, and so we don't get as much intense light, and so it's cooler throughout those seasonal periods. Fall, spring, winter. Let me go ahead and see if we can answer this question as a group with your small partners, and then we'll share out. What would happen to the seasons on our planet if the Earth was not tilted at all, but was just straight up and down like this? What would happen if this was our model of the sun and it wasn't tilted? It was just like this. It's still rotating. It's still revolving, but what would happen with the seasons? Would there be any seasons on the planet? Please turn with your pair share partner and let's see what you can reason out as a group, please. I'm going to check on the back lab area. Kanye, you got to focus, man. This is Marianne. She is. Do you need her? Is she coming back? Okay, thank you. Yep, bye. Man, you have to go to the guidance office to Chanel, please. All right, so what do we think would happen in this situation, sweeties? Yep. Okay, so he's saying there'd just be one season all the way across our entire planet? So everything would be summer? Everything would be fall? So I would have fall here, where we get the most direct sunlight. It would just be like what? It would just be warmer at the poles. Indirect up there. Colder there. So we still have up here indirect sunlight. Okay, so we're going to have what up there, you think? It won't be as warm, so it'll be cold. Maybe it would be something like a winter up in this area. And it would be winter all year long. Okay, and it would be winter down here all year long. What about in the middle? Summer all year long. What about in this general direction and this? It would be fall or spring. This is where we live. And it would be fall or spring weather. Because you would not have a changing of the angles of the light. That angle of light would always be the same. It would never change from this angle. It would never change from this angle. So you would always have the same temperatures year round. Now, would it vary a little bit? Like maybe some days it'd be, a little warmer, maybe a little cooler. Yes, but it would always be that fall or springtime weather where we live. If you lived a little bit farther up where this angle of light would never change, it would always be that season, whatever it is. Now, imagine tourism, right? Hey, I want to go experience summer. Okay, let me travel to where summertime is. You'd have to travel to where fall is. You'd have to travel to where winter is. Now, if you wanted to go skiing, you could just go to a very tall mountain, and even if they were at the equator, would that tall mountain still have snow? Yes, because the higher up the mountain you go, the colder it gets. Nice job, darling. The colder it gets. All right. So that is the cause for the seasons. I have a 5-minute video that I want us to go ahead and watch. This video is a direct correlation to what it was that we did on Friday in the. Yep. You guys are talking and you make plans to go visit him next summer.
So, anytime next summer works for you? Yep. Whenever's best for you.
All right, so think about the lab we just did. July rolls around and you hop on a plane for your Australian vacation. Imagine your surprise when you show up at his house and he tells you,
What are you doing here, mate? It's the middle of winter.
and then you say,
Winter? It's the middle of summer back in America.
and your friend's like,
I don't know what to tell you. July is winter for us. Okay, I don't get this. How can it be summer in America and winter in Australia at the same time?
that's a great question. I think we can help you out with that. To answer this question, we have to zoom way back and start with a top-down look at the Earth's orbit around the sun. Oh, by the way, everything you see in this video isn't to the correct scale. Now, the Earth's orbit isn't a perfect circle. It's actually an ellipse. You usually see it drawn like this. Lots of people think,
Hey, this must be why we have seasons. When the Earth is close to the sun, we have summer. And when the Earth is far away from the sun, we have winter.
but that's actually not true. That's one of the biggest misconceptions, right? So if you thought that in the beginning of this, you are not alone. Everybody thinks that because of the way we draw it. That's not truly how exaggerated the ellipse is, okay? It's not truly how exaggerated. This is a misconception. This is wrong. If this was true, Australia would have summertime the same time that we do, and they don't. It's direct opposite. And it's not.
No, that's not the case.
Exactly. The way we draw Earth's orbit here is really exaggerated. People just draw it that way to highlight the extreme. In actuality, there's a relatively small difference between the Earth's closest and furthest points from the sun. If we draw Earth's orbit with the correct shape, it looks like this. You can see it's actually pretty circular, but it's not perfect. So it's not the closeness of the Earth to the sun that causes the seasons. To see what's actually at work, we have to look at the orbit from the side. In our side view, the Earth is revolving around the sun in this orbital plane here. It takes 1 year to go through a full orbit, 365 days. Remember, at the same time, Earth is rotating on its axis once every day. The important thing, for the seasons at least, is that the Earth actually isn't straight up and down. It's tilted at an angle of 23.5 degrees. So when the Earth is on this side of the sun, the northern hemisphere is angled away from the sun. The southern hemisphere is angled toward the sun. When the Earth is revolving around the sun, it stays tilted in the same position. The axis doesn't wiggle around or anything. It just stays fixed in a certain direction. So when the Earth is over here, the northern hemisphere is angled towards the sun, and the southern hemisphere is angled away. When the hemisphere is angled towards the sun's rays hit it directly. That's what's happening in the northern hemisphere here. But when the hemisphere is angled away from the sun, like the southern hemisphere here, the sun's rays hit it indirectly.
Okay, so what difference does direct or indirect sunlight make?
Oh, there's a huge difference. Let's take a look with a simple experiment. In this experiment, we're going to use a flashlight to simulate the sun. Say that the flashlight is a particular sunbeam. If it's shining directly, all its energy is concentrated in a certain area. But if the sunbeam is shining indirectly, the area is larger. This means that the same amount of energy is spread out over a larger area. Okay, so pause. With that second, more spread out light, would it be cooler or warmer than the first circle that they did? Turn and talk with your pair share partner about that. Would it be cooler or warmer with that second spread out circle? What do we think? What do you think? Yeah. Do you think this one that they created right here, this second one, it's the same energy coming out of the flashlight, but it's covering now more area? Would this be warmer or colder than this in the middle? It would. It'd be cooler. It'd be cooler because you've got the same energy, but it's shared over a much larger area. So each one of those points on the paper in this general area would actually be a cooler temperature. Nice job. All right.
So, in a particular point on the paper, it feels colder in the indirect sunbeam than in the direct sunbeam. And the more indirect the sunbeam, the larger the area. It's important to note that the amount of energy in the sunbeam is always the same. It's not changing. However, if it's spread out over a larger area, we feel it less. Let's take a look at what this means for the Earth. Here we have a globe that's angled at about 23.5 degrees. It's June, so the northern hemisphere is angled towards the sun. If we shine the flashlight directly on the northern hemisphere, we see it illuminates a certain area. But when we move the flashlight to shine indirectly on the southern hemisphere, we see that it's illuminating a larger area, just like we talked about. So let's put it all together. When the northern hemisphere is tilted towards the sun, it's receiving direct sunlight. It feels warmer, which means it's summer there. And the southern hemisphere is receiving indirect sunlight, which means it feels cooler. That's winter. 6 months later, when the Earth is on the other side of the sun, we have the opposite. It's the southern hemisphere receiving direct sunlight, so it's summer there. And the northern hemisphere is receiving indirect sunlight, so they're having winter. And now you know the reason for the season.
Awesome. So it's not how close the Earth is to the sun that matters, but instead it's the tilt of the Earth.
Which is also why it's winter in Australia at the same time as it's summer in America.
You got it.
Well, I think this is the most educational vacation I've ever had.
And there's so much more to talk about. Did you know that the Earth...
You know, I actually think I'm good for now.
Oh, okay.
No, I'm
Yeah,
okay.
question.
Go ahead. What's your question, darling?
So, what time of the year would it be the same?
Good question. Those are called the equinoxes. And so equinox would be when the axis is not pointing towards or away. Okay, there's the North Star. Right now it's pointed away from the sun towards the North Star. Over here, it's still pointing towards the North Star, but it's tilted towards the sun. And so when it's like this is going to be equinox. This is going to be spring or summer, depending on what hemisphere you're in. It's got 12 hours of daylight and 12 hours of nighttime when it rotates like this, okay? So it's just evenly distributed. Yep, good question. That happens over here, and that also happens when it's over here. So through one whole year, you're gonna have a spring equinox, you're gonna have a winter, fall equinox, and then a summer. Winter, spring, summer, fall. All right? So that's a really good question. Now, let's go back, please, to your deeper look at the seasons. You have a check for understanding. On the bottom, number 1, it says the Earth is closest to the sun in January. Aron, come back, bud. But January is cold in the northern hemisphere. Why? Turn with the person next to you, please, and see if you can talk that out. A, B, or C? Looking at that question, please. This will give me an opportunity to check really quick on my people in the back.
We went through this last time. Okay.
All right.
What
do we think, ladies and gentlemen? If you could please help me out. Logan, thank you very much. The Earth is closest to the sun in January, but January is cold in the northern hemisphere. Why, Logan?
I said the northern hemisphere is tilted away from the sun during this time.
Yeah, so A, the northern hemisphere is tilted away from the sun. And so that means it's getting indirect sunlight. The temperatures are cooler. Let's look at number 2. As the angle of light increases from the equator to the poles, energy from the sun does what? Okay? Is the sun increasing? Is the sun staying the same? Or is the sun decreasing? Tell me about the energy from the sun. I don't even have to read the rest of it. Yeah, the sun's energy always stays the same. So because the sun's energy always stays the same, which one of these has to be right? B, because it's the only one that says the energy from the sun is not increasing or decreasing. However, it says B, it stays the same, but the energy is shared over a larger area of land. That's why we have the temperature changes that we do from the equator to the poles. How's that? Great. The next thing we're doing is we're doing a little deeper look, my dears. And so if you could please find this piece of paper in your packets. You have this piece of paper in your packet. It says, let's take a deeper look at the seasons. Do you not have this? Okay. Now, this packet was broken in half, and some of my classes in the morning did not get the second half of the packet. But if you are missing the second half of the packet, I can give that to you now. Oh, okay. Do you need a bunch?
302. 302.
Yeah. Good question. That question, Anthony, did you write down the answers that we did we talk about the answer for what would happen if it was just straight up and down? Okay. So what would happen if it was just straight up and down? Let's go back really quick to that one part in the pink section. Right here, what would happen if it, to the seasons, if the earth was not tilted but straight up and down? We said there would be no change. There would be no change to seasons in a particular area. For example, the northern hemisphere would be, if it was Iowa, fall or spring year round. There would be no change. If it was winter, it would always be winter. If it was summer, it would always be summer. Okay, just like what we have right down here. In Iowa, it would be like fall, spring weather all the time. There would be no change in the temperatures. Not that you'd complain. I really like fall and spring weather personally. Do you like summer? It's nice. All right. So there would be no change in seasons in a particular area. We would still have seasons, but you'd have to travel to those seasons around the world. Good? All right, so let's go ahead and look at a deeper look. We're going to draw on this activity how the sun's rays will hit the earth on different days. We're going to shade areas where the sunlight is not currently hitting. These are going to be areas that are experiencing nighttime. We're going to label the season in the northern and the southern hemisphere, and we're going to circle areas that never have a sunset or a sunrise. Shh. If you're coming in, please quietly come in, and you need to get this piece of paper out in front of you. It's called Taking a Deeper Look at the Seasons. Everybody should have this in their packet. I want you to hold on to your seasons lab, please. Again, if you are coming in, please do not speak to the people that are already in here, and we are focused on what it is that we are doing. So let's go ahead and start with what's called the vernal equinox. Demarius had asked earlier, what would happen where it's equal daylight and equal nighttime, 12 hours of day and 12 hours of night? That would happen here in vernal equinox in the northern hemisphere. This is spring. When we're talking vernal, that is an oldie Latin word for spring. So for our first example, let's go ahead and show that the most direct sunlight would be located here. So we're going to write most direct. Most direct sunlight is going to be concentrated at the equator and a little above the equator and a little below the equator. Our least direct sunlight, when we are positioned at this area, least direct, would be located at the top area and then also at the bottom. Least direct, or you can go ahead and write indirect. Okay, so what we're going to have is we would have springtime up here in the northern hemisphere. So I'm going to write the word spring. Down here, you would have fall because the north and the south are direct opposite of each other. We're going to have daytime over here where the sun is shining. So nighttime is going to be back here. I'll write the word night. And then I'm going to shade all of this in, showing that this would be daytime, nighttime and daytime. Now, again, this is rotating, so that's okay. You're okay. Thank you. All right. So that is going to be the spring or the vernal equinox. Now, let's still imagine we are in the northern hemisphere, and after springtime for us comes what season? Summer. After spring comes summer. So we're going to go ahead and go to the summer solstice, which is going to be around June 21st. Summer solstice is when we have the longest day of the year. That's daytime hours. We will still have 24 hours in a day, but it's just the longest daytime hours and the shortest nighttime without sunlight. So let's go ahead and draw what will happen here. Imagine, if you will, that we are tilted. This would be like the tilt. This then would be night. If you could please stop talking to the people around you. It's really dark. I know. I'm so sorry. So then this would be nighttime over here. And if you want to write night over to the side and then point, you definitely can. And in this case now, we have most direct hitting a bit higher up on the planet. We're still always going to have the area around the equators get a lot of sunlight, and we are getting more direct up here. We are getting the least direct then in this general area. This would be if you are stationed at the South Pole, and there's a research station there. My dad was stationed there in the Navy. This is where you have 24 hours of nighttime. It kind of gets just a little bit where maybe the sun's going to come up, but it doesn't. And so down here, let's circle where we are never going to have a sunrise, okay, during this time period. It's 24 hours of darkness.
Is there anywhere that is 25?
Yes, at the very top at this point of the poles, we are going to have 24 hours of daylight. Yay. 24 hours of daylight sounds wonderful, except if you're trying to sleep. And your biorhythms, right, as a human being, you need to have that period of darkness in order to get you in the right kind of sleep rhythms. So 24 hours of daylight, like if you're living in Alaska, you know, this is when the sun kind of goes down, but it's always sort of that dusk, right? That's as much as it gets. And then it'll get nice and bright again during the daytime. So we never really have nighttime. What, dear? Yeah, you'd have to get like room darkening shades. Yeah. All right. Oh, so let's go ahead and say on this one, we have summer up in this area. So let's write summer. And then we have winter down here. And again, I'm so sorry that your photocopies are a little bit dark. It's difficult for you to see. All right. I'll make this a bit smaller so that we can fit more on. So now, for us in the Northern Hemisphere, after summer, what season do we move into? So let's go ahead to the autumnal. This is autumn. This is fall for us. And let's see what we have. This is a period of time where we have another equinox. So we have equal day and night. So this is going to be night over here, and we have day over on the other side. Okay, but it's 12 and 12. We are back to this area where we have least direct light, equally shared at the poles. And then in the middle, we have the most direct light. "12 hours of daytime, 12 hours of nighttime." And so at this particular point of our revolution around the sun, we do have a daytime and a nighttime at the North Pole and the South Pole. All right, after fall in the Northern Hemisphere, we have winter. You're struggling, man. You're on the struggle bus over there. We have winter.
At least I'm on the bus.
You are on the bus. God, I love you. That's right. So now we are tilted in this direction so that we've got, you're on the bus. So now we've got most direct light is going to be hitting this area. Most direct light. And we get the least direct then is going to be in this area. Oops, sorry, I forgot over here to write that this would be fall in the Northern Hemisphere and springtime in the Southern Hemisphere. So since it was springtime in the Southern Hemisphere over in this location, that means we're moving into summertime over here in the Southern Hemisphere. And now wintertime is happening in the Northern Hemisphere because we get less or the least direct sun rays. Now we are back to a situation again. This is when my dad was stationed at the South Pole. He always was stationed down there during eternal summer. So this would be 24 hours of daylight. 24, oops, I should say hours of daylight. They don't put you down in the South Pole when there's 24 hours of nighttime. That's cruel. Yep. Beg your pardon? Thank you. So then at the top, we have 24 hours of night. We have time. Please don't pack up yet. Now, I think that it would be a great fun for me to give you something like this on the exam, shade it in, and say, okay, let's see if you can figure out what, season this would be or something like that. Yeah, no. Where you just fill it in. All right, ladies and gentlemen, listen to me for a minute. If you can hear me, please clap once. If you are somebody that was in the back room and you are working on the Seasons Lab, I will be here after school to help you, or tomorrow morning you can come see me, or during lunch I'm open all fourth hour. I would love to be able to come and see you. Tomorrow in my class, we have a test. on seasons and climate factors. I'm telling you, there is going to be a graph on it. It's going to be a quiz that you are going to be taking tomorrow on seasons and climate factors.